Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today I am going to deliver the lecture on nuclear magnetic resonance spectroscopy. Like all other spectroscopic techniques, NMR spectroscopy involves the interaction of the material being examined with electromagnetic radiation. Remember the last lecture, mass spectrometry. I told you in the mass spectrometry there is no use of any electromagnetic radiation because the mass spectrometry is the count of the mass, right? So it doesn't use any of the radiation from electromagnetic spectrum. But in case of nuclear magnetic resonance spectroscopy, it uses the radiation from electromagnetic radiation. So what is spectroscopy? So spectroscopy is the study of molecular structure and dynamic through absorption, emission and scattering of light. One can also define the spectroscopy is the study of interaction between the radiation, which can be from the electromagnetic radiation or light, as well as particle radiation and the matter. So this is called the this is called the spectroscopy. Alternatively, the spectrometry is the technique through which doesn't use any electromagnetic radiation. It uses the fast beam of electrons which can strike the molecule and molecule become charged. That type of the energy is used in mass spectrometry. So this is the electromagnetic radiation spectrum. So in this spectrum you can see the radiations, various radiation, radio frequency radiations, microwave, infrared, visible, ultraviolet, X-rays, gamma rays, and after gamma rays there is a cosmic rays. So generally the cosmic rays lies here. The cosmic rays have very high frequency and the short wavelength, right? So this is all the rays which have the short wavelength but very high frequency. So generally this gamma rays or cosmic rays falls at the highest energy and end of the known electromagnetic spectrum, and it involves the greater frequencies of this radiation. The radiation at the left hand side, for example, this one is the microwave or radio waves or radio frequency. So these radio frequencies, which is the type of the radiation that is concerned us in NMR spectroscopy. Generally, the NMR spectroscopy uses this radiation which is called the radio frequency radiation. That is occur at the lowest energy. It is a lowest energy or low frequency and the larger wavelength. So this is region of the electromagnetic radiation used by the NMR spectroscopy. So the NMR spectroscopy is arguably the most powerful and broadly applicable technique for the structure determination available to organic chemistry. So what is the nuclear magnetic resonance spectroscopy? The nuclear magnetic spectroscopy is the study of the molecules, by recording the interaction of radio frequency electromagnetic radiation. So the interaction of radio frequency electromagnetic radiation with the nuclei of the molecule which is placed in a strong magnetic field. So these molecules placed in a strong magnetic field, and then the radio frequency provided, and there is a radio frequency interaction of interaction with the molecule nuclei. As a result of that, we can get the information about the molecule. So it is simply the study of the interaction of radio frequency electromagnetic radiation with the nuclei of the molecule. That's why it is called nuclear magnetic resonance spectroscopy, because there is an interaction of the radio frequency with the nuclei of the molecule, which is placed under strong magnetic field. So that this indeed the structure of the compound can often be determined using the nuclear magnetic resonance spectroscopy alone. Although in the practice, structural determination is generally accomplished through a combination of technique that includes nuclear magnetic resonance and IR spectroscopy and mass spectrometry. So other than the mass spectrometry and IR spectroscopy, this technique also play a very important role in order to elucidate the structure of the molecule, or to give the information about the molecular structure. So you can see here this is a spectroscope, different spectroscopic technique which help in the structural elucidation of the compound. For example, this ultraviolet visible radiation, which can affect the molecule by changing in the electronic level, energy level within the molecule, and it gives the information about the pi electron system. Infrared is also one of the radiation which is absorbed by the molecule, and as a result of this absorption of this infrared radiation, the change in the vibrational and rotational movement of the molecule takes place. As a result of this, we can get the information about the functional group. This technique detect the information about the functional group. For example, different functional group, for example, the carbonyl, for example, the amino group, for example, the hydroxyl group. So, about these functional group, we can get the information through infrared radiation. Another radiation, which is the microwave radiation, which spin the electrons and give the information about the free radical. Fourth one is the technique or radiation which is used for in case of the structure elucidation is nuclear magnetic resonance radio frequency. So what this radio frequency does is, it when the nuclei is placed under the strong magnetic field, so there is a spin change of the nuclei take place after the absorption of radio frequency. So as a result of this, we get the information about the electronic environment of the molecule, their numbers, and the number of neighboring atoms. So these are the different techniques which give the information about the structure of the compound. So as you can see the name, right, nuclear magnetic resonance, the abbreviation is NMR. So this abbreviation tell us the most of the information about what this technique is all about. N is for nuclear, M is for magnetic, and R is for resonance. So this technique is the study of nuclear spin. All the nuclei of an atom they are spinning, right? So it gives the information about the nuclear spin when we place the molecule under the influence of the magnetic field, and the after the placing the molecule in under the strong magnetic field, the resonance phenomena occur. So what is the resonance is the to record the resulting resonance of the nuclear magnetic spin through absorption of radio frequency. So after the absorption of radio frequency, the resonance phenomena will occur. As a result, we can get the information about the nuclei of the molecule. So this nuclear magnetic resonance spectroscopy involves the study of interaction between the electromagnetic radiation and nuclei of atom. So a wide variety of nuclei can be detected using the nuclear magnetic resonance spectroscopy, including including the H1, which is the hydrogen, right? Carbon 13, N15, which is nitrogen isotope, fluorine F19, and P31 phosphorus isotope. So in practice, the proton NMR, which is H hydrogen NMR, which we will discuss later, and the carbon 13 means carbon NMR, in order to detect the carbon in a molecule, are the most often technique used by the organic chemists. So because of the hydrogen and carbon are the primary constituents of organic compounds. So this is actually what happening in order to record the nuclear magnetic resonance spectrum of any compound. So you can see this one is the excitation pulse, which is actually the radio frequency radiation, which is also called the excitation pulse. This is the atom or molecule under investigation. So when this radio frequency radiation strike the molecule, so the spin of the nuclei will occur, and as a result of this, it emits the information about the structure of the molecule, and which is recorded in the form of the spectrum, which is called the nuclear magnetic resonance spectrum. So this is only the overview. Later we will see how the NMR spectrum look like and what are the important things in the NMR spectrum. So the most important thing is, in case of the NMR spectrum, is the information about the nuclei of an atom. So you can see the frequency of the molecule observed, and this is the intensity. So here you can see there are different type of the nuclei. For example, chloride, for example, carbon, for example, this hydrogen. So all the nuclei have different frequencies, right? Meaning that the information about these nuclei can be observed at a particular frequency, which is under the radio frequency. So meaning that in order to get the information about the hydrogen, it needs different frequency under radio frequency radiation. For chloride, it required another frequency, different frequency. For activation of carbon, it required different frequency. So that's why in the spectrum we can get the different peaks of different nuclei. For example, the chloride have different peak, different resonance, different frequency. Carbon have different frequency. Hydrogen have different frequency. So there is a different frequency required in order to get the information about the different nuclei. So this was the first high resonance proton NMR spectrum observed, which was the proton spectrum of ethanol. So there are the three, they have observed the three different lines in case of ethanol spectrum. So if you see the this ethanol, so in case of the ethanol, in case of ethanol, you can see ethanol contains CH3, CH2 and OH. So this is the formula of the ethanol. So if you see the ethanol, right? So how many different type of hydrogen in case of the ethanol? 1, 2 and 3. Three different type of hydrogen. One is the CH3 methyl, one is CH2 methylene, and one is the hydrogen attached with oxygen. So there are three different type of hydrogen, which different type of hydrogen nuclei in this molecule. So that's why they absorb three different peak, 1, 2 and 3 in case of the proton NMR spectrum. Proton is because of hydrogen. Hydrogen, you see the hydrogen. Hydrogen has inside one proton and there is one electron outside in case of hydrogen. So this technique in this technique is the technique in which the radio frequency interaction with the nuclei of an atom. So in case of the hydrogen, the nuclei of an atom contain one proton. That's why in case of the hydrogen, we say the proton and a nuclear magnetic resonance spectrum. So wherever we use the word a proton, it means we are talking about the hydrogen, because in the hydrogen nuclei there is only one proton, right? So that's why they have found out that ethanol contains three different type of proton in a molecule. This was the first spectrum of the ethanol observed. So NMR spectroscopy history, you can see the NMR spectroscopy also have the importance in case of the scientific history. These two scientists, which is the Flux Bloch and the Edward Mills Purcell, they got the Nobel Prize in the field of nuclear magnetic resonance spectroscopy. So they in which topic they received the Nobel Prize in Physics in 1952 for their development of new method for nuclear magnetic precision measurement and discoveries in connection therewith. So they have found out the different. They developed the new method, which is the nuclear magnetic precision, in order to get the information about the molecule. So this is also the summary of the development of NMR. So development of NMR was started in 1940. First observation of nuclear magnetic resonance in solid and liquid, and then after this you can see 1950, 60 and 70 and up to 2000 plus the use of high sensitive superconducting probe is used. Generally the magnet which is used in case of the nuclear magnetic resonance spectroscopy, the magnet is superconducting magnet. So that magnet, the magnet is under the superconducting liquid. So you can see that this the journey of the nuclear magnetic resonance spectroscopy started in 1940. Just you have to remember just for your information that how important this technique is. The question arises, why bother learning NMR? So NMR spectroscopy help in various fields of the chemistry as well as biochemistry and other fields. So it helps in structural elucidation in the field of nature product chemistry, in synthetic organic chemistry, in order to find out the structure of the molecule. It play an important role in the study of dynamic process. For example, in order to study the reaction kinetics, in order to study the equilibrium, chemical or etc. It helps in the structure elucidation study of the proteins, DNA, protein-DNA complex, polysaccharides. It helps in drug designing process also, in order to do the structure activity relationship studies, and then in the medical field, in order to get the brain NMR, which is called the magnetic resonance imaging. So now move to the fundamentals of NMR spectroscopy. So here I will tell you how the NMR spectroscopic signal generated. So the most important phenomena which is related to the nuclear magnetic resonance spectroscopy is the nuclear spin, which is also called the spin quantum number. So recall your knowledge related to the quantum number. So there are four type of quantum number. Number one is principal quantum number. Number two is the azimuthal quantum number. Number three is magnetic quantum number, and fourth one is the spin quantum number. So these quantum numbers give the information about the structure of the atom. So what is the nuclear spin? The nuclear spin is the turn or cause to turn or whirl around quickly. So spin quantum number is the quantum number that parameterizes the spin of a given particle. So meaning that it gives the spin information about the nuclei or spin information about the particle. So NMR involves the detailed manipulation of nuclear spin, because all the nuclei. Remember, nucleus is a singular and nuclei is a plural. So the nucleus as a spin means rotation. So the nuclei of an atom is always rotating. So this nucleus and spin quantum number, which is abbreviated as I. So if you see that m is equal to z plus n. M is the mass number, z is the number of an proton, and n is the number of neutron. So if for example m is even, what do you mean by means mass number is even, then the spin quantum number will be 0, right? If the mass number is even, then the spin quantum number of that atom will also be 0, right? For example, in case of oxygen 16, right? So in 16 means 8 proton and 8 neutron. 8 plus 8 is 16. If both are even and even, the spin quantum number in case of oxygen 16 will be 0. In case of carbon 12, 6 electrons or 6 protons and 6 neutrons, right? So that will be equal to 12. So means mass number will be even, then the spin quantum number also will be the 0. So if the spin quantum number is 0, then these nuclei cannot be detected through nuclear magnetic resonance spectroscopy. So this nuclei can be designated as and not NMR observable nuclei. If the mass number is uneven, right? Means uneven or the number of neutron is uneven. So then the spin quantum number will be 1, 2 and 3. Just you have to remember only this. If mass m is even, then I will be 0. right? If the this Z is uneven and N is uneven, then also the I will be the 1, 2 or 3, right? So the example will be the H2, which is the second isotope of the hydrogen, right, deuterium, right? And in case of the H14, this one also the in this N14, 7 is Z and 7 is neutron, right? That will be equal to N14. So that nuclei can have the quadrupole movement. They have resulted in broad lines. It gives the broad line in NMR spectrum, right? So if the M is uneven, means uneven means it can be the odd, right? So I, which is the spin quantum number, will be half, 1 by 2, 3 by 2, 5 by 2. So in the example is H1, which is the proton, carbon 13, N15, F19, P31. All these nuclei have the M, which is the mass number, is uneven, right? So this one 13, 15, 19, 31, all are uneven. The spin quantum number of all these nuclei, we are talking about the nuclei because this is nuclear magnetic resonance. It gives the information about the nuclei of an atom. That's why we are only talking about the nuclei of an atom or nucleus of an atom. So the spin quantum number of that nuclei or these nuclei will be half, and it gives the sharp line and good for NMR. Means these all nuclei are NMR observable nuclei. So these all nuclei are NMR observable nuclei, right? So just you have to remember that if M is E1, right, so I will be 0, I will be 0. So in case of the M E1, if Z in E1 and N in E1, then I is equal to 0. If Z is uneven, N is uneven, I will be 1, 2 and 3. If M is uneven, in case of hydrogen, carbon 13, in case of N15, the spin quantum number will be half. They are generally good for NMR. So you have to remember that these nuclei are good for NMR active, right? So if the I will be half, right, spin quantum number, they are good for the NMR. For aluminum and other nuclei, their spin quantum number is larger than the half. They are the quadrupole movement, right? This is only for your information. What you have to remember is if M is uneven, I is equal to half. For these nuclei, they are good for the nuclei. If M is even, I will be equal to 0. They are not NMR observable nuclei. This is in case of this oxygen and carbon 13. So NMR spin quantum number. So the NMR, the spin if NMR this quantum number is not equal to 0, these nuclei are called the magnetically active nuclei, or nucleus is magnetically active, which is only possible in case of this H1, which is the proton, carbon 13, N15, F19, P31. I is equal to half. Their quantum spin number is not equal to 0. They are good for NMR. They can be observed through NMR spectroscopy spectroscopy. So they will be observed at different frequencies, right? Because every nuclei have different property, right? So they can observe at different radio frequencies. All nuclei have different frequencies. Remember, proton have different frequency, F19 have different frequency, P31 have different frequency, carbon 13 have different frequency, and N15 have different frequency, right? So one and normally at one frequency only one nuclei can be observed. If let's say for you are interested in find out how many different types of the proton in a nuclei, right? So specific frequency for the proton has been given and the information about the proton will be recorded in NMR spectrum. So now what's happening in the NMR spectrometer, right? So these are all are the nuclei. These are all are the nuclei, and these are the magnetic movements of the nuclei. These are the movement of the nuclei, right? So what happens? These all are nuclei are in random motion. These are in random motion when these nuclei are outside the strong magnetic field. That's why it has B naught is equal to 0, because these nuclei are not under influence of strong magnetic field. Right? If this nuclei placed under the strong magnetic field, that's why if there is B naught is greater than 0, then these nuclei will be oriented toward the magnetic field or against the magnetic field. So when we place the sample into the NMR spectrometer, before placing the sample into the NMR spectrometer, orientation of the nuclei is like this, right? They have the random orientation. When we place the nuclei or place the molecule or place the sample into the strong magnetic field, they are highly oriented against the magnetic field or toward the magnetic field. Then what happens is, after placing into the magnetic field, before placing the magnetic field, this is B naught is equal to 0, the orbital will be degenerated. Right? When we place the nuclei into the magnetic field, the orbital will be generated. Right? One has the lower energy orbital and the second one is the high energy orbital, right? So this will generate it once we put the molecule into the strong magnetic field, and these are the nuclei of an atom, right? Remember, we are only interested in nuclei of an atom, right? So these orbitals are generated when the molecule is placed under the strong magnetic field. That's why you can see degenerate without magnetic field, and if the molecule is under the influence of magnetic field, then the orbital will be generated. This increase in magnetic field strength, the orbital will be generated. Delta E is equal to K B naught is equal to, this one is the Planck constant and frequency. So this orbital is generated when strong magnetic field applied, right? So some nuclei will be oriented toward the magnetic field, some nuclei will be disaligned with the magnetic field, right? So this is the spin state at different energy level, which is only generated when the nuclei placed under the strong magnetic field. So the nuclear spin state of hydrogen nuclei. So you can see this one, hydrogen have spin quantum number half. Some of the nuclei have half spin quantum number, positive half spin quantum number, while some of them having the negative or minus spin quantum number. One is oriented toward the magnetic field, that's why it is half. the some will be, or some nuclei will orientate opposite the magnetic field. That's why it has negative R. So spin is positively charged nuclei generated in a magnetic moment vector. So that is vector in magnetic moment. It tell us that the movement of the nuclei is toward the magnetic field. So this will be possible when the nuclei placed under the strong magnetic field. So after the effect of the magnetic field, what will happen when the spin active hydrogen atom is placed in a strong magnetic field, it start moving means it has some frequency and it start preceding, right? So that is called it precedes with its own frequency, right? So this is only possible when the nuclei is placed under the strong magnetic field, right? So all nuclei will precede with its own precessional frequency. So what is precessional frequency? The frequency at which the nuclei precedes. This is called the precessional frequency. And when it will be possible? When the nuclei is placed under the magnetic field. So after the placing the nuclei into the strong magnetic field, then we applied the radio frequency to the system, right? So this is the radio frequency. So this is frequency from 40 to 600 megahertz within the region of radio frequency, right? So when this radio frequency observed by the nuclei, what will happen? Nuclei will jump from lower spin state to the this higher spin state, right? So this will be only possible when radio frequency applied to the system. After the absorption of energy, then only this excitation will occur. So this excitation will occur when the system observes the radio frequency. So then this phenomena is called the resonance, absorption of energy by spinning nuclei, right? Remember, some of the nuclei spinning against the magnetic field, some of the nuclei spin toward the magnetic field, right? So after the absorption of the radio frequency, right, the absorption of energy takes place, and as a result of this, resonance will occur. This is called the resonance. This is only possible when the system absorbs the radio frequency. So after this radio frequency absorption, the phenomena of relaxation occur, right? The energy the radio frequency provided to the system is only for 10 to 20 microseconds, right? After that the radio frequency is switched off, right? After the switching of the radio frequency, then the phenomena of relaxation will occur, which is called relaxation process in NMR, which is very important in order to get the information about the nuclei of an atom. So the excitation of relaxation of nuclei is the phenomena. In that phenomena, the excited nuclei return back to the downward transition state. The nuclei will relax to the lower energy state. This you can see the nuclei, right? This one is the nuclei. It absorbs spinning nuclei. Spinning nuclei when absorb the energy or absorb the radio frequency, and it will excite it, right? One, it absorbs the energy. So after switching off the radio frequency, it will relax back to the lower energy state. So during this relaxing back to lower energy state, it will emit some of the information, right? So this phenomena is called relaxation process in NMR, right? So once it return back to the lower energy level, this phenomena is called the relaxation process in NMR. So there are two types of the relaxation process in NMR. One is the longitudinal or spin lattice relaxation, which is the T1, and second one is transverse spin relaxation, which is called the T2. So in case of longitudinal relaxation, what happens? Because it emits the energy. So the emitted energy can transfer in two ways. Either it transfer to the environment or energy transfer to the neighboring proton or neighboring atom. Right? So there are two possibilities where this energy or relaxation process give the information about the environment of the proton, right? So the spin lattice or longitudinal relaxation T1 involves the transfer of energy, whether transfer of energy to the lattice or the environment, or transfer the information to the neighboring proton. If it transfer the energy to the surrounding, that relaxation is called spin lattice relaxation. So it gives the information about the environment of the proton. So if it transfers the energy to the neighboring proton or among the or nearby proton, so that relaxation is called spin relaxation or transverse relaxation. So remember, there are two types of relaxation in NMR. One is spin lattice and second one is spin relaxation. So this is because the energy which is emitted after the relaxation, right? It emitted in two ways. Either it emitted to the surrounding, or it emitted or transferred to the surrounding, or it transferred to the neighboring proton. So after that one, we can get the spectrum or the information about the energy like this. You can see this information or like this wave information, right? So this is the information regarding the proton, right? So this is the time domain spectrum, and usually spectrum is recorded like this, right? So this is called the time domain spectrum. So this time domain is converted into the frequency domain through Fourier transformation, because the time domain spectrum is not possible to read. It should convert into the frequency domain. This is called the Fourier transformation. So this one is only after the relaxation process, and then after the computational processing through Fourier transformation, this time domain convert into frequency domain. This is the frequency of particular nuclei. So this process is called the free induction decay. So the signal decay away due to the interaction with the surrounding. So this is called the free induction decay, FID. So the free induction decay is the result of the relaxation process. So this free induction decay is converted into the frequency domain by Fourier transformation method. So Fourier transformation or FT of this time domain signal produce the frequency domain of the signal, and through this frequency we can get the information about the nuclei of an atom present in a molecule. So this is called the free induction decay, which is recorded as a result of the relaxation process. and through computational method or Fourier transformation mathematical method, it will convert into the frequency domain. So this is the NMR spectrum of phenyl acetone. So phenyl and this one is the acetone. So first of all, uh, you have to look that how many different type of the proton in the phenyl acetone, right? Number one. If you see the structure of the phenyl acetone, so it has one, two, and this is the phenyl proton, right? So there are three different type of the protons in case of phenyl acetone, right? One is this methyl, one is CH2 methylene, and third one is the 5 proton, which is the phenyl proton. So that's why it has 3, 1, 2 and 3 peaks of the phenyl acetone in NMR spectrum of the phenyl acetone, right? So forget about this 0, 1, that I will let you know uh, uh, later why there is a peak at 0, right? So there are three different type of protons in case of phenyl acetone. So each different type of proton come at a different place, right? So meaning that this methyl CH2 and this phenyl is placed at a different place in NMR spectrum. So later you will know why these proton place at a different or having the different frequencies. So what are these lines are? These are the frequencies of these proton. Frequency of the methyl, frequency of the CH2 which is methylene, and this one is the frequency of the phenyl proton. So it tell us the frequencies. NMR spectrum tell us the frequencies of the different type of proton present in a molecule. Now the second most important part of this lecture is NMR spectrum, right? In this part we will see how the NMR spectrum looks like and what information we can get from the NMR spectrum. So the NMR spectrum composed of three most important components. Number one is chemical shift, number two is integration, and number three is spin splitting. The chemical shift is actually the signals in the proton NMR or NMR spectrum. So which you can say the frequency of particular uh, proton or particular nuclei. The second one is integration, which tell us the ratio of number of particular nuclei. And third one is the spin splitting, which is the signal splitting in case of the neighboring proton. So one by one we will see all these major components of NMR spectrum. So if you see in case of this one NMR, this one chemical shift. So chemical shift is the signals in NMR spectrum, this one or this one. Integration tell us how many number of the proton particular nuclei at specific signal. So this one is the integration, right? And then the spin splitting is the splitting of each signal, which we'll see one by one, right? So the splitting of the NMR signals. So first we'll see what is the chemical shift. So chemical shift is actually the variation in precision radio or precisional resonance frequency is referred to as the chemical shift. So meaning that the precisional frequency of the proton or the chemical shift or the particular value of the of any nuclei, right, which is called the chemical shift. Or one can define the chemical shift is a chemical shift in a nuclear magnetic resonance spectrum resulting from dimagnetic shielding to the nuclei by the surrounding electrons. So what, so there is the surrounding electrons, right, by which the nuclei is shielded, right. So there is a shift in the magnetic resonance spectrum. That shift also called the chemical shift. Or you can define the chemical shift, the radio frequency or the frequency of the proton of, or the frequency of the signal is also known as the chemical shift, right. Or the precessional frequency of particular proton or particular nuclei of a signal is also known as the chemical shift. So meaning that these signals are the frequency of particular nuclei. So this one is spectrum is the spectrum of ethanol, right. So how many proton in ethanol? So one is, you can see, hydroxyl proton, the second one is methylene proton, third one is the methyl proton. So there are three different type of the proton, that's why it has three different signals. So later we will see why these signals are separated, right, why they have different frequencies, because x-axis tell us the frequency of particular nuclei, right. So this is the, in case of NMR you have to see, or you have to more emphasize on this x-axis, which tell us the frequency of the proton, right. So at this stage you can only remember how many signals generated by the NMR, right, of generated by the NMR in the case of ethanol. So first you have to see how many protons in case of different type of the proton in case of ethanol. Ethanol has hydroxyl proton, right, methanol has methylene CH2, right, and the third one is this methyl proton. So that's why it has three different type of protons, so three signals. So the chemical shift, of the proton expressed in the frequency hertz, is expressed in frequency unit, right, or this is called a hertz also. So but there is some disadvantages of using the unit hertz, is that it is proportional to the strength of magnetic field. So what is the strength of magnetic field? In NMR spectrometer we generally use different strength of the magnets, right. Sometimes we use 400 megahertz, 500 megahertz, 600 megahertz. These are the different strength of the magnets, right. So just you can uh, understand like this, there's a power of the magnet. So 400 megahertz, 500 megahertz, 600 megahertz, these are the power of the magnets. So if the power of the magnet increase, then the value of the particular proton also increase in case of the hertz, right. But so there is some confusion in case of using the hertz or using the unit which is called the parts per million. So there are two particular units used in case of the, to express the chemical shift, hertz, and the second one is parts per million. In case of the hertz is directly proportional to the strength of the magnet. If the strength of the magnet increase, right, so the hertz value will be changed. So that's why there is a disadvantages of using the unit hertz in case of the expressing the chemical shift. So so meaning that so spectrometer with different magnetic field will have different chemical shift. So that's why generally we use the unit which is parts per million instead of the hertz. So just you have to remember why we are not why generally hertz not used, because it change with the change of the magnetic field. So the ppm is used in order to avoid the chemical shift changes with respect to the magnetic field. So generally the most proton in case of the organic compounds, because we are interested in pharmaceutical organic compounds, so that's why uh, here the word used organic compound, uh, to which they are bounded, right. So the chemical compound, generally this ppm scale or nmr scale, you can say nmr scale, is used within 14 ppm of TMS. TMS is actually we use the internal standard in case of NMR, which is tetramethyl silane. Then that's value, and its value is always at 0. So NMR signal is start from 0 to 14 generally in case of organic compound. So in this case you can only remember that NMR scale or ppm NMR scale is started from 0 and it go up to the 14 or 15 parts per million, right, in case of organic compounds. So you can see, so this one is x-axis, which tell us the frequency of particular proton, right. We are only interested in protons, right, means hydrogen, right. So just you have to remember only the nuclei now we are interested in is hydrogen. Hydrogen, and in hydrogen generally we express the hydrogen uh, in in proton, because there is one proton in the nuclei of the hydrogen, right. So you can see aliphatic compounds generally comes in between 0 to 2. In case of alcohols, proton and alpha ketone is come in between 0 to 5. Olefins generally lie at 5 ppm, 5 to 7 ppm. And then the aromatic amines generally lies in between the 77 to 10, the generally aromatic compound. And then the acid and aldehyde generally lies in between 10 to 15. So later we will discuss more and more about the chemical shift and why these signals, why these class of the compound have different ppm value or different frequency. So so this one is just an overview of NMR spectrum, right? So this region which is near to 0 is generally the region is the upfield region, or having the all the have the lower frequency. So this one region is called, this region which is near to 0, right, over to toward your right hand side is designated as upfield or shielded region or low frequency. So this one region is the low frequency region. As we move from right to the left, so right to the left in NMR spectrum, so the region which is away from 0 and towards your left is the downfield region or decreasing the shielding region, which is called de-shielded region or high frequency. So this region which is away from the 0 is the downfield region or decreased shielding or de-shielding region or high frequency region. So this region is high frequency region with respect to the shielding region, and the TMS tetramethyl silane is always come at 0. So just you have to remember that the this region which is near to 0, right, and toward your right hand side is upfield region and lower frequency or lower frequency region, and the region which have the value away from, or region away from the 0, right, meanings 5 7 5 6 7 8 and toward the 10, this region is called the downfield region or high frequency region, right. And this signal is the solvent signal generally, or this one is chloroform, which having the value 7.28, right. So just in this slide you have to remember that this is the chemical shift scale. The region which is near to 0 is the low frequency region, and the region which is away from 0 is high frequency region. So now we will discuss the chemical shift of some of the particular proton or particular um, classes of the organic compound. For example, you can see the table is started from the NMR scale started from 0 to 13, right. So different different. So this one is alcohol. So this one is alcohol. Different alcohol region started from 0.5 to 5, right? And then this one is the alkane, which is near the at a low frequency region. And then this one is the bromide attached with the carbon. The proton which is attached with the carbon, which has the bromide having the frequency is nearly this 4.1, because this bromide is electronegative element, right? So it pulls the electron from the carbon, and carbon also have the high electronegativity as compared to the proton. So that's why the first this broma high electronegative element pulls the electron from the carbon, and carbon pulls the electron from the proton. As a result of this proton, the electron revolve around the nucleus of the proton will be de-shielded. The nucleus of the proton will be de-shielded. So that's why it's always come at de-shielded region or high frequency region. You can see it is away from zero. So this region is low frequency region, and this region is the region which is away from the zero is the high frequency region. So this is the reason why the proton which is attached with the carbon, which is having the high electronegative element, having the high frequency because of de-shielding, right? The same the phenomena or the same concept applied on the this chloride also. Chloride is a more electronegative as compared to carbon. So chloride pulls the electron from the carbon, carbon pulls the electron from the hydrogen, and as a result of the hydrogen nuclei will be de-shielded. That's why it come at high frequency de-shielded region. The same phenomena applied at the applied as the this alcohol or ether, right? Because it has this olefin, right? Olefin also have the uh, uh, it has a pulling effect, right? So that's why all the electrons revolve around these pi electrons, right? So as a result of this hydrogen will be de-shielded. That's why it come at high frequency de-shielded region. The same the phenomena applied at this aldehyde and carboxylic acid. You can see oxygen have is high electronegative as compared to the carbon. So and then this is a this carbonyl resonance between this pi electron resonance between this this oxygen and this oxygen, right? So as a result of this, the electron which is shared by the same electron which shared by the oxygen and the carbon, right, pulls by this resonance, right? As a result, the nucleus of this hydrogen will be de-shielded. As a result, as a result of this, the value of this proton which is attached with the carboxylic group is come at de-shielded high frequency region, right? So the same phenomena applied or wherever you can see the electronegative element is attached, they all comes at de-shielded high frequency region. So that's how just you have to remember. What you have to remember in this slide is the simple concept of why the some signals come at low frequency region, and why some signals have comes at the high frequency de-shielded region. The simple concept is if any electronegative element attached, all the proton signal will become a de-shielded high frequency region. Later we will do some of the exercises, then you will understand more better. So here the chemical shift scale, how to convert the hertz into the ppm. So this is the formula, right? So this is the chemical shift. So formula is the observed shift from TMS, tetramethylsilane in hertz, multiplied by 10 to the power 6, and operating frequency of the instrument in hertz, meaning the strength of the magnet. So for example, the question is, if the chemical shift of the benzene proton is 2181 hertz and the experiment performed at 300 megahertz instrument, this is the strength of the magnet, which is constant, which is depend upon what magnet are you using in case of the NMR, right? So then the chemical shift expressed in the unit of ppm, parts per million. So this one is 2181 hertz is the this value of the proton, this value of the aromatic proton or benzene proton lies at 2181, which is multiplied by 10 to the power 6, and this is the strength of the magnet, 300 megahertz. So here you have to convert the megahertz into hertz, then you will find the answer there, 7.27 in ppm, right? So the chemical shift of the benzene proton in 60 megahertz in the instrument in 436 hertz. So you can see here you have we have measured the value of benzene proton in 300 megahertz, which is 2181. In case of the benzene proton value in case of the in case of 60 megahertz, the value will be 436. So that's why you can see the we not usually use the hertz unit, because the value of the proton is continuously changing with the hertz or the strength of the magnet. So you can see that the chemical shift of the benzene proton in 60 hertz. So this one is 60 multiplied by 10 to the power 6 hertz. Convert megahertz into hertz, and therefore 436 hertz multiplied by 10 to the power 6, which is a part of the formula. You can see the value in case of the ppm is same as in case of 300 megahertz. That's why you can see we use the parts per million instead of the using the hertz. So in NMR we generally use the internal standard. So the internal standard which is commonly used in NMR is tetramethylsilane, which is usually called the TMS. So the need for the standard is to compare the signals with the TMS. So TMS signal always, or TMS peak, single peak always come at 0 ppm. So always we see the proton frequency or the nucleus frequency with respect to this reference, which is the TMS. So this is tetramethylsilane. So this silicon, and 1 2 3 4 tetramethylsilane used as an internal standard in you commonly in organic compound we use the TMS as an internal standard. So why the TMS is used? Because it is chemically inert, not react with our compound or our material, right? It is symmetrical. It has the symmetrical molecule, and volatile. Boiling point is 27 degrees Celsius. So it evaporates from the material very easily and soluble in most of the organic solvent. So this is the reason why we use the TMS, right? So uh, in order to use this internal standard, the standard should be chemically inert. So and then the second reason is it gave a single intense sharp peak, absorption peak in NMR spectrum, and its proton are always shielded, means near to 0 or 0 than almost all organic proton, right? So this is the two reasons why we use TMS with respect to its chemical nature, and second one with respect to its the origin of the peak in NMR spectrum. So in NMR spectrum always the TMS peak will be lie at 0 ppm. The peak will be single peak, right, and sharp peak and then it always come at shielded region. So regarding using the solvent in case of the NMR experiment, right? Yes, the sample is dissolved in the solvent. Any kind of the solvent use? Yes, we use the solvent. Most preferred solvent is the deuterated solvent. So what do you mean by the deuterated solvent, right? So most of the organic compounds are soluble in the organic solvent. We use the solvent, but the solvent is the deuterated solvent. So what is mean by the deuterated solvent is the NMR spectrum are usually measured using the solution of the substance being investigated. So it is important that the solvent itself does not contain any sample hydrogen. For example, chloroform. See, the chloroform is CHCl3, right? So we are looking for the proton in a sample. So we usually prefer there should be no proton in a solvent. So we replace this hydrogen with the deuterium. That's why it is called the deuterated solvent. So in case of the chloroform, we use the deuterated chloroform, which is CdCl3. So for example, in case of the benzene, right, if we use the solvent benzene, so the all the hydrogens of the benzene replaced by the deuterium C6D6. This is called the deuterated solvent. So we generally use the deuterated solvent in case of the NMR analysis. So use of or the second thing is, or you can use any solvent which doesn't have any proton, for example carbon tetrachloride, right? So this is the preference we gave in case of the solvent, right? It should we avoid the proton and or replace the proton with the deuterium. Why use the deuterium? Because deuterium does not produce any peak in a NMR spectrum, and we can easily analyze our sample proton, our sample nuclei through NMR analysis. Deuterium atom have because deuterium atom have different magnetic properties other from this ordinary hydrogen. That's why we does not observed any peak in the NMR spectrum in case of the deuterated solvent. Now we will do some of the practice. How many numbers of the proton in an H1 NMR spectrum? So H1 NMR spectrum, why? Because hydrogen contain only one proton inside the nucleus, right? And through this technique we are only observing the or interested in this nuclei of an atom. So in case of the hydrogen, there is one proton inside the nucleus. That's why it has a 1H or H1 proton, H1 NMR spectrum nuclear or 1H nuclear magnetic resonance spectrum. So now we will see some of the examples how many signals are generally produced by the NMR in these type of the compounds. For example, in case of this molecule which is dimethyl ether, right? So in case of the dimethyl ether, we can get only one NMR signal because this methyls and this methyl has same chemical environment. They are the same protons, right? Because this is attached with also oxygen and this one is also attached with the oxygen. So all the protons are equivalent. That's why we observe one NMR signal. In case of this one, this ethyl chloride. So in case of ethyl chloride, we have two different protons, right? One in one type of the proton, it's attached with the carbon, which is attached with the chloride, and this one CH3 is attached with CH2. So these two are different type of the proton, two different type of protons. That's why it has two NMR signal. In case of this compound, right, in case of this compound you have to count how many how many number of the signals in this one, how many different type of the proton. So that will be related to how many NMR signal, right? So how many different type of the proton, you can see this one CH3 attached with CH2, but this CH3 is attached with O, different chemical environment. So that's why this CH3 is have different signal as compared to this one, because this CH3 is directly attached with oxygen. So one type of proton, this one CH2 is attached with oxygen, right? It is not CH3, right? So this is one second type of the proton, and this one is the third type of the proton. So three different type of the proton. That's why in NMR it has three different NMR signal. In case of the in case of this compound, you can see three signals, one this one, 2 and 3 different types. This CH2 is attached with bromide, this CH2 attached with CH2 and CH3, different chemical environment, and this CH3 is attached with CH2 and other 3 protons. That's why it has 3 different type of signal. This one bromide, this one compound having 2 different signal, right? This one methyls and this two methyls are attached with same CH that is attached with the bromide. So that's why it has same chemical environment. Only this proton have different chemical environment because this attached with the carbon which contains this bromide. It has 2 NMR signal. This one also have 3 signal, 1, 2 and 3. This one have 1 signal, the same as this one. This one compound having the uh, 2 signal. Why? Because these all methyls are attached with same carbon which is attached with the oxygen. That's why these 3 methyls have same chemical environment, right? And then this CH3 attached with the oxygen, it has different chemical environment. That's why all 1 and 2 signals. This one compound also have the 2 signal because this attached with the CH which is attached with the chloride 2, 1 and 2 signal. This one is also 2 signal because these 2 methyls attached with the same carbon which is attached with this olefin, right? So 2 signal. This one have 1 signal because these 2 protons attached with the carbon which have same bromide, right? So that's why it has 1 signal. This one is aromatic compound which is benzene. All protons are equivalent protons, right? All have same chemical environment. That's why it has 1 signal. This one is aromatic compound with a nitro group, right? So the proton which is near to the nitro group have different chemical environment, and the proton which is away from the this nitro group have different chemical environment. So it is depend upon how far these protons are, right? So these the proton which is near to this nitro group have the different chemical environment. That's why one type of signal, this one little bit away from the nitro group, second and different chemical environment as compared to this proton. This proton is far away from nitro group, that it has different chemical environment. So 1, 2 and 3. So it's simply depend upon how far the protons are. So the protons which is near to the nitro group is having different chemical environment, and if you keep away from this nitro, the environment will be different, and the group which is far away from nitro group will have different signals. That's why it has 3 signal in NMR spectrum. So this one also same, more exercise, right? 2 different type of the proton or 1 type of proton. Answer 1 type of proton, right? Because this CH2 is attached with chloride and this also CH2 attached with same chemical environment. That's why it has 1 type of proton, 1 NMR signal. In case of this one, right? So you can see this CH2 attached with chloride, right? Different chemical environment. This CH2 attached with CH2 and CH2, right? Different chemical environment. This CH2 attached with the the carbon which is attached with the bromide, different chemical environment. So 3 NMR signal. So the same as here, it has different type of the proton, which is proton attached with methoxy, and then this one is attached with a double bond carbonyl group. This is actually carbonyl group. Two different type of protons, so that's why 2 NMR signal. In case of this one also, the same 3 different type, right? In case of 1,1 dichloroethylene, two different proton or one, no, it has or same chemical environment, because adjacent carbon contain chloride, adjacent carbon contain chloride, but this carbon only attached with the carbon with the same environment. That's why it has 1 NMR signal. This one also same, right? Also same, but what is the difference is the neighboring carbon contain chloride, neighboring carbon contain bromide. So it has different chemical environment. It has different chemical environment in case of the cis 2 chloride and cis 2 bromide. So different chemical environment, because this chloride group is influence on the environment of the proton. That's why it has 2 NMR signal. Now we come to the diamagnetic shielding. So why these the chemical shift are different in case of different type of the chemical environment. This is called the diamagnetic shielding. So far we have seen how many signals. Now we will see why these signals are appear at different ppm or different delta value, different chemical shift. So this is called the diamagnetic shielding. So what is diamagnetic shielding? The electronic clouds around the proton, right? So electronic clouds around the proton attached to any X nuclei, means any chloride, bromide, iodide, or oxygen, or any carbonyl group, right? So it's, it generates the secondary magnetic field, which is referred as diamagnetic shielding or diamagnetic anisotropy, right? Because you can see, understand from here, these are the electrons, same electrons shared by this X and H. If this one is more electronegative, it will withdraw the electron from the proton. So as a result, this proton will be the nuclei of the proton will be no more shielded with the this electron. That's why it will appear at de-shielded region. Nuclei will be de-shielded because electron is withdrawn by a more electronegative element, right? So for example, you can see why is more electronegative. It pulls the electron from the hydrogen, and the hydrogen will be de-shielded, and it come at higher frequency, right? So this is called the diamagnetic shielding. So this one is the shielded region or a fielded region or low frequency region, and this one is the de-shielded region, downfield region, because of magnetic because of diamagnetic shielding. So that now the chemically equivalent, the proton which have same chemical environments, these are called the chemically equivalent protons or chemically equivalent nuclei. Two or more nuclei are said to be chemically equivalent when they have identical chemical environment. In case of this one, this is benzene. All protons have same chemical environment. That's why it has one peak, right? One peak, and then only one peak. It means same chemical environment. So two or more nuclei that are in identical environment have same chemical shift or resonance frequency, therefore give only one proton NMR signal. So if they have same chemical environment, it will give the single peak, or this they are identical chemical the identical chemical shift. So here you can see the example of the identical protons or non-identical one, which the proton which have same chemical environment and the proton which have different chemical environment. So you can, first of all, you have to see that how many different type of protons are in this molecule, right? So this molecule have methyl CH3, this molecule has CH2, and this molecule have the aromatic protons. So how many different type of the proton? 3. 1, 2 and 3, meaning there will be 3 different signals. So this, now the second thing is the why these signals are at different ppm, different frequency, is depend upon the dimagnetic um shielding, right? So you can see this methyl is attached with the carbonyl, right? This but this CH2 is attached with aromatic or benzene ring, right? And then it's attached with the oxygen, right? So this CH2 is attached with two different parts which have more electronegative as environment as compared to this CH3. This CH3 is attached with only carbonyl, which has more electronegative as compared to this, but this CH2 is attached with this aromatic ring, which has also electron withdrawal effect. Oxygen also have electron withdrawal effect. It will in this the proton of this carbon will be more de-shielded as compared to this one. So that's why this CH3 will become at lower frequency region, and this one is come at high frequency region, because the electrons between these proton are being withdrawn by this oxygen as well as this aromatic region. And the third one is this aromatic region always come at de-shielded region, because the electron which is involved in sharing between carbon and oxygen are involved in aromaticity, right? So that's why the proton of these aromatic compounds are more de-shielded as compared to other proton, because their electrons are shield this involved in stabilizing the aromaticity, right? So that's why the proton of the aromatic compounds or aromatic protons are come at high frequency region or de-shielded region. This so that's how you can um, decide that where the chemical shift. Simply only you have to apply the concept, right? Not necessary where what the specific value is, but you have to decide where which proton can become at shielded region, which will be the come at de-shielded region. Is only depend upon the chemical environment around the proton. So this is also inductive effect. The proton which is attached with the more electronegative element, or with the element which have the more withdrawal effect, electron withdrawal effect, will come at high frequency region, and the proton which is attached with the electron donating group, they always come at shielded region or low frequency region, right? So this one is electron donating group, always come at shielded region. So you can see once the proton is attached with oxygen and phenolic group, it's having the de-shielded environment, or having these groups have electron withdrawal effect as compared to the amino group. That's why it come at de-shielded high frequency region. The carboxylic acid is most de-shielded one, because the most of the electrons are involved in stabilizing the carboxylate group. So as a result of this, the proton of this carboxylic acid is the most de-shielded proton. That's why it come at the almost 11 or 12 ppm. So this is, you have to simply apply this concept, that electron withdrawal group de-shielded region, electron donating group shielded or upfield region, or the low frequency region. So this is the same as hybridization, as in the sense of hybridization, right? So this one is sp3 hybridized group, this one is sp2 hybridized group, and this one also have the sp2 hybridized group, which is mostly attached, the proton is attached with electron withdrawal group. So this is comparison between different groups, which have the different hybridization. In case of acidic proton, in case of aldehydic, phenolic, alcohol, amino group, amide group, and enols, they have different chemical shape, right? So just you have to remember the concept that if electron withdrawal group, it will come at d shielded region, high frequency region. If they have electron donating group, right, or the element which donates the electron, it means they are contributing to stabilize or contributing to shield the proton, it will come at shielded region. In case of the aromatic compound, so I told you that in case of the aromatic compound, the protons of the aromatic ring are more de-shielded as compared to other protons. Why? Because these aromatic clouds generating the ring current in case of this aromatic compound, because this ring current is because of the pi electrons. So this is the reason the proton of this aromatic ring are more de-shielded as compared to the other functional group protons, right? So because of the ring current effect, and ring current effect is because of these aromatic pi electron clouds. So this is same, you can see now, and previously we see how many different signals. Now we will see that which proton have the most de-shielded protons, right? Because of the presence of any inductive group, or any electronegative group, or any group which have the electron withdrawal effect, right? In case of the fluoride, you can see it appear at 4.5 de-shielded region. Because of this fluoride, it has more electronegative. In case of the chloride is less electronegative as compared to fluoride. It is less de-shielded as compared to the proton which is attached with the fluoride. In case of the bromide is less electronegative as compared to the fluoride. That's why it come as less de-shielding region as compared to the fluoride. In case of the iodide is the most less electronegative as compared to the fluoride, chloride, and bromide. That's why it appeared at shielded region as compared to the proton which is attached with the fluoride, right? Here you can see, in case of this compound which has nitro group attached with CH2, CH2, right? So nitro group also have electron withdrawal effect. It has also electron withdrawal effect. Because of electron withdrawal effect, this CH2 is the most de-shielded region, and then after this less effect on this CH2 as compared to this one, it become less de-shielded as compared to this one. This proton CH3 is the most shielded proton. In case of aromatic, this is the equivalent protons because of this ring current. That's why it appeared at the de-shielded region. So there are different type of the functional group. In case of this aldehydic, you can see it appeared at 9 ppm because of this carbonyl inductive effect, right? Carbonyl inductive effect. This appeared at 9 ppm de-shielded region. So in case of, you can see this is the one NMR spectrum of this compound. How many different type of the proton in this one compound? First you have to see, right? One is these aromatic protons, right? And then second one is this CH3 have same chemical environment, and this CH. 1, 2 and 3 different type of signal in case of this compound. And why they are at a very different place, right? Because you can see this one aromatic protons always come at de-shielded region, this one de-shielded region, and then after this one the less de-shielded as compared to this one is this one CH, which is attached with aromatic. So this one is second de-shielded one, and most shielded one is this methyl, right, which is away from this aromatic ring. So that's why it appear at near to the one which is the shielded region. Now we come to the second part, which is the integration. We have already covered the chemical shift, how many different type of the proton and why their chemical shift are different, right? Now we will see second part or component of NMR spectrum is integration. So what integration tell us is to find the ratio of number of the proton, number of the hydrogen atom in different chemical environment. So in proton NMR spectrum, the area under NMR resonance is proportional to the number of hydrogen which that resonance repeated. Means it tell us that how many number of the protons are having the same chemical shift. This is called the integration. So by measuring or integrating the different NMR resonances, information regarding the relative number of the chemically distinct hydrogen can be found. So it found that the how many protons having the same chemical environment on specific chemical shift uh, uh, by this integration process. So integration only gives the information of relative number of different type of proton. So in this case you can see aromatic proton 1 2 3 4 5. So this integration is at this ppm 5 proton have same chemical environment. This is called the integration. This one, this molecule, you can see this molecule, this has how many different type of proton? 1 2 and 3 different type of, that's why it's 1 2 and 3 different type of proton, right? So in this one, the first one CH3 have how many different type of how many same protons which have say the same chemical shift? Only 3 protons have same chemical shift. So that's why integration tell us 3 proton have same chemical shift. This one CH2, right? The second shielded de-shielded as compared to this aromatic compound. 2 protons have same chemical shift. So it can also 2 proton have same chemical shift, which is at CH2, and 5 proton have same chemical shift, which is at around 7.3 ppm. So integration tell us how many, integration tell us that how many different type of the hydrogen having the or they are the chemically distinct environment. Now the third part of the NMR spectrum, or third component of the NMR spectrum, is signal splitting, which is also called the spin splitting. So just I brief you what we have already covered, right? In NMR spectrum, number one, chemical shift, and number two, the integration of NMR spectrum. Chemical shift tell us that how many different type of the proton or how many different signals, and why these signals are come at different ppm value or different delta value, right? The second one is integration tell us how many protons lies on having the same chemical environment, right? The third one is the signal splitting, or the signal splitting which which is caused by the effect of the magnetic field of the proton on nearby atom or proton. So it tell us the environment of the molecule, right? Because of this environment, the signal of with the signal of a specific chemical shift will be split into different splitting pattern. So the signal splitting is because of the coupling of the spin of the two protons, meaning tell us the environment of the protons. It is also designated as the multiplicity, right? So the spin coupling effects are transferred primarily through bonding electrons, and not usually observed if the coupled protons are separated by more than 3 sigma bonds. So it is, remember I told you in the relaxation phenomena, right? Longitudinal relaxation and transverse relaxation, right? So uh, the spin splitting, the spin, the transfer of the energy, right, to the lattice and transfer of the energy to the neighboring proton. So this spin coupling is because of the transfer of energy to the neighboring proton. It gives the information about the neighboring proton, right? So it is the also called the multiplicity. It can be calculated from this formula, right, which is m multiplicity is equal to 2 n l plus 1. N is the number of equivalent nuclei. I is the spin quantum number, this one, right? So for example, in case of the nuclei in case of the nuclei which have the spin quantum number half, that is for proton, or in case of the carbon 13 also. So the following equation simplified to, the equation will be simplified like this, right? M is equal to n plus 1. So this is the general formula, and this is the formula for the proton which have the spin quantum number half. M is equal to n plus 1, right? So this one you can just put the half here, right? So then 2 to 2 will be cancel out, then only the left is n plus 1. So multiplicity, or the number of lines in a signal. So m is tell us the number of the lines. Later we will see what it mean by the lines. And n is the number of equivalent nuclei. How many number of the equivalent nuclei in a nearby proton. So for example, spin splitting. The common splitting for the which is observed in NMR spectrum is singlet, doublet, triplet, quartet, quintet, sextet, and septet. Right? Means single one line is called the singlet, two lines is doublet, three lines triplet, four lines quartet, and then 5 lines is quintet, 6 line is sextet, and 7 line is septet. So this is how the splitting occur. For example, this is the proton Ha, right? So you can see Ha, the near carbon contain how many proton? Near carbon contain only one proton, right? So Ha, one equivalent proton, adjacent proton is 1, Hb, right? So if you put in the formula, right, if you put the formula, then there will be the two peaks, right? The formula is m is equal to n plus 1. Adjacent proton, adjacent carbon contain, or the adjacent how many protons is 1. 1 plus 1, 2. That's why it has two peaks, which is the doublet, right? Hb, the one adjacent proton, which is Ha. So put in the formula m is equal to n plus 1, right? So 1 plus 1, 2. 2 peaks, that will be doublet. Doublet is because the adjacent, the adjacent carbon contain only one proton. You can come here. Second one, Ha, the adjacent carbon contain 2 proton. 2 plus 1, 3. Then the Ha give the information about neighboring proton, that it contain 2 proton. 3 peak is because of the formula 2 plus 1, 3. Triplet means adjacent carbon have 2 proton. Peak pair is triplet. And what information this will tell us about this proton, right? So adjacent carbon, adjacent environment contain 1 proton, right? So 1 plus 1, 2. So this gives the information about the adjacent proton by splitting up into 2 peaks as a doublet. This one, Ha and Hb, two different type of the proton, right? So HA, two adjacent protons, HB, right? Two adjacent HB protons, right? 2 plus 1, 3. 3 peaks, triplet. And it gives the information about this one and this proton, which is HA, two adjacent HA proton, 2 plus 1, 3, 3 peaks, triplet. Right? So spin gives the information about the adjacent proton environment. So how many protons are attached with the adjacent carbon? How many protons are at adjacent carbon or adjacent element? So this one you can see, this one HA. So HA, how many protons attached with the nearby carbon which is near to HA is 3. 3 plus 1, 4. 4 peaks wanted. So it will give 4 peaks information about the neighboring protons. HB have two adjacent proton, right? 2 plus 1 is 3. 3 peaks, triplet. So quantet, this will give the quantet information about this, and this will split into triplet and give the information about the nearby proton. This one HA, here HA have give the information about this methyl, right? So this one is HA, adjacent proton, how many? 3 adjacent HB protons, right? 3 HB proton. It gives the information about nearby proton. So 3 plus 1, 4, right? So this is quartet, right? And then this will give the information about adjacent proton. How many? 1 adjacent HA proton only, right? 1 plus 1, 2. That's why it is doublet. So this is called the spin splitting, which gives the information about the adjacent or information about the neighboring carbon or neighboring proton environment. This one, ethyl group, right? So ethyl group, this one, it will give the information about this CH2, and this will give the information about this CH3, right? So this CH2 nearby proton, how many nearby proton is 2. 2 plus 1, 3. That's why it is split into triplet. And this one CH2 nearby proton is 3. 3 plus 1, 4. It will split into quartet. This one. So it gives the info related to the chemical shift. It is split into it gives the information about that the I am attached with the carbon which is attached with the iodide group, which is electronegative. My chemical shift is this one, but the nearby environment is the nearby carbon connect or nearby carbon contain 3 proton. That's why I meant splitting into the 4 or quartet, right? So it gives the information about its chemical environment and the environment nearby the proton. This one, the proton NMR signal of 2-bromopropane. So first of all, you can see how many different type of protons, right? 1 and 2, two different signals, right? The 2 different signals, right? Now we come to the second part is the chemical shift, which is the most deshielded and which is the most shielded one, right? The proton which is attached with the bromide is the most deshielded one, which is appeared at around 4 to 4.2 or 3, and most shielded one is methyl, which is away from the bromide, is come at shielded region, right? So this is the 2. Number 3 is the splitting, right? So this CH2, this one CH is attached with 2 methyl, right? 2 methyl is means it contain how many methyl? 1 hydrogen, 1, 2 and 3, 4, 5 and 6. 6 plus 1, 7. It gives the information about its own chemical shift, its own environment, and the information about how many nearby protons are. So how many? 1, 2, 3, 4, 5, 6. 6 plus 1, 7. So 7, this signal will be split into this septate, right? 7. It's 1, 2, 3, 4, 5, 6 and 7. This is septate. And then after this methyl gives the information about its own environment, that this I am attached with shielded proton, right? Shielded proton. So my chemical shift is this one, right? But the nearby I have only one proton. One plus one, two. These both protons have same chemical environment. So 1 plus 1, 2, doublet. So this one is doublet. The proton spectrum of ethanol, how many different type of the protons? 1, 2 and 3. And which proton is the most deshielded one? Is this one, right? Because it attached with the oxygen, right? But these two protons are attached. This one CH2 also attached with oxygen. This one is also attached with oxygen. With respect to this CH3, both are deshielded, right? So 3 single 1, 2 and 3, right? And then this one gives the information about the environment nearby protons. C2, 2 protons, 2 plus 1, 3. 3 is triplet. So this one is triplet, CH3. This CH2 gives the information about this CH3. 3 plus 1 is 4. Because this one is quartet. This one is quartet because of this presence of this CH3. Right, and always the alcoholic proton is OH. It is only one proton. It doesn't have any carbon with the hydrogen. Carbon with hydrogen. It's always come at the singlet peak. 2-heptanone. So 2-heptanone is, this is the chemical formula of the 2-heptanone, right? How many different type of the proton? 2-heptanone is, you can see 1, 2, 3, 4, 5, 6, 7. This one part and this part of the molecule is same, right? So this one methyl has same chemical environment as this one. This CH2 have same chemical environment as this CH2. This CH2 have same chemical environment of as this one, but as compared to this one, it's attached with the carbonyl electron withdrawal effect, electron withdrawal group, right? So how many signals? Right, 1, 2 and 3, 1, 2 and 3. Which one is the most shielded one? Which is very far away from the carbonyl group or any inductive effect group, right? CH3. After that, less effect. The more effect is CH2, and the most effective one or more inductive effect at this CH2, right? It is the most deshielded one as compared to this CH3. So this one is the most deshielded one. After that, less deshielded, and most shielded one is this one. This one is split it into how many single? Nearby 2 proton, 2 plus 1, 3, triplet. This one is split into how many? Nearby carbon have 1, 2, 3, 4, 5. 5 plus 1, 6. This one is the sextet, right? This one CH2, nearby proton is 2. 2 plus 1 is 3. 3 means triplet, right? So this 4-heptanone, in case of the 4-heptanone, how many singles? 1, 2, 3, 1, 2 and 3, and different chemical shift because of the different chemical environment, and it is split, which is split into different splitting pattern, which tell us the environment of the adjacent carbon. In case of the isopropyl benzene, right? Benzene, this one, right? How many different type of proton? One different. This one is same chemical environment, right? One type of proton, second type of proton, and third type of proton. So always generally the aromatic ring, either it have the single peak or it come at jungle of peaks, but you have to assign this jungle of peaks or multiplicity as a single peak in case of the aromatic compound, right? This is only one peak, generally appear as a multiplicity also, but forget about this one. So this one, so how many single? 1, 2 and 3. 1, 2 and 3, right? Most shielded one is this methyls, right? After that one, this one deshielded as compared to this one, and most deshielded one is this aromatic protons, right? So this one CH3 is this one, and then this proton is at 2.8, and this aromatic proton will become at de-shielded region, which is 7.3, right? And the nearby proton, which is how many protons, is one proton. 1 plus 1 is 2, doublet. This metal is split into doublet, right? And then this proton will be split into how many protons? Split into how many signal? 1 2 3 4 5 6. 6 plus 1 7, septate. Split into septate. And then this one is the aromatic signal, which is come at 7.3. So how many signals? 1 2 3, right? And then each signal is split into doublet, and then this one is split into septate, right? And this one is split into the singlet or multiplicity in case of the aromatic. This is the NMR spectrum of phenacetin. This is a molecular structure. First you have to identify how many protons, different type of the protons in a molecule. So the CH3, NH, CH2, CH3, and aromatic protons. So how many? 1 2 3 4 5. Five different type of the protons are present in this molecule, right? So meaning there will be 5 different signals, right? Number 1, this is for the aromatic proton. Number 2, number 3, number 4, and number 5. 5 signals, right? So first you have to identify how many signals, right? So second, why these signals are have different chemical shift? Because of the presence of the different functional group, right? So CH3 is present along, is near to this carbonyl group, right? And then NH is present this near to the carbonyl group as well as aromatic. So the electron withdrawal effect or inductive effect is more at CNH as compared to CH3, right? And if you can see here, CH3 and CH2. So this CH3 is connected with CH2, right? So meaning that this CH3 is not connected with any inductive group, right? So most shielded one, this CH3, this one, right? After that one is this CH2 is connected with oxygen, right? And this one is this CH3 is connected with carbonyl, right? So this one is the second most second number shielded molecule, right? And then this part, right? NH is most de-shielded one. So this is the signal of NH, right? Aromatic proton, this one, and then CH2 is connected with oxygen, right? So that's why it is come at 4 ppm, bit far away from this shielded proton of this CH3. So CH3, the now we will talk about the splitting of the signal. CH3 adjacent there is no proton, so meaning that 0 plus 1 is 1 singlet, right? So this one is singlet, right? This CH3 is the neighboring carbon have 2 proton, 2 plus 1 3, triplet, so this one is the triplet, right? And then this CH2 neighboring carbon have 3 proton, 3 plus 1 4, right? Quartet, so this one is the quartet. And this is the jungle of peaks for the aromatic ring, right? So you don't need to uh, define these peaks, right? This is the aromatic proton peaks, para substitution, right? Di substitution peaks. And NH there is adjacent, there is no proton with this carbonyl, right? That's why it has single proton peak, right? So that's how you have to define the number of the protons and why the chemical shift are different, and then how why they are split it into the triplet, quartet, and singlet. So now this is a spectrum of isobutyric acid. So isobutyric acid um, have the carboxylic acid, right, group. So remember what I told you, that the carboxylic proton is the most de-shielded proton, which is appear at around 12 or 11 or 12, right? So how many different type of the proton? These metals have same chemical environment, right? A, and then this one's B, and this one C. So how many different type of proton? 3. 1 2 and 3, right? So 1, 2 and 3. Now we talk about the different chemical shift. So these two metals is connect with the carbon, right, which does not have, which have the carbonyl group adjacent carbon, but this two methyl group is not connected with the any inductive group, right, or electronegative atom, right? So this one is the most shielded one, right, the most shielded one, this one. And then after this proton is connected with a carbon which has a electronegative property, right, or the electron withdrawal effect, right? So this is the second most second um, shielded one, right? So and then after this a most de-shielded one, this carboxylic acid, right? So now the third is splitting pattern, right? So these protons, right, so these 6 methyl proton, the adjacent carbon have only one proton, 1 plus 1 2 doublet. So these two methods is split into doublets. It gives the information about the neighboring proton, right? And then this proton is split into how many? The adjacent carbon have how many proton? 1 2 3 4 5 6. 6 plus 1 7. This is septate, so 7 peaks. It gives the information about that it adjacent carbon have 6 protons, right? And then carboxylic proton always have the singlet because adjacent carbon have no peak, 0 plus 1, then it's appeared as a singlet, right? So these things you have to define in case of explaining any NMR spectrum, explaining the NMR spectrum of any compound, right? So this is spectrum of this dibromopropane, right? So how many different type of proton, right? A and B, two different type of the proton, right? This is connected with bromine and this, so two different type of protons, so that's why it has two signal, right? And then adjacent have two proton, 2 plus 1 3, so a triplet, right? So this one is the triplet, right? And this proton have this carbon have the how many proton adjacent? 1 2 3 4, 4 plus 1 5. This one is the 5 is quintet, so this one is the quintet, right? So that's how you have to explain that how many signals appear, and then why they are have the chemical different chemical shift, right? Because in this case the bromo is attached, so meaning that high electronegative element attached, that's why the proton appeared at d-shielded region, so that is a d-shielded region. And this one proton is a bit shielded as compared to the CH2 proton which attached with the bromide. So this is the proton spectrum of amino benzoic acid. So how many different type of the proton in this compound, right? Number 1, right, number 1, and then number 2 NH2 proton, right? And then these two protons have different chemical environment as compared to these two, right? 1 2 3 and 4, 1 2 3 and 4, four different signals in case of these compound, and different chemical shift because of the presence of the inductive group. Carboxylic acid mostly shielded, this one is the aromatic protons, these two are the aromatic protons. Carboxylic acid have more inductive effect, that's why these protons are more de-shielded, this one. And then this one is a bit shielded as compared to this proton, right, because it is near to the electron donating group. This is the for the this ortho to NH2 group, and this one is for the NH group peak. This adjacent there is no proton, right? That's why 0 plus 1 singlet, that's why it appeared as singlet, right? So and then this one is the proton spectrum of one compound, so it is splitting pattern, right? So how many different type of the proton? 1 2 3 4 and 5. So that's how they are split it into different splitting pattern. This one is split it into triplet, this one is split it into singlet because with this one is split it into singlet because of adjacent carbon there is no proton, right? And then this proton split into triplet because adjacent carbon have two proton, 2 plus 1 3, This one is split it into triplet because adjacent carbon 2 proton, 2 plus 1 3 triplet. This one also same chemical environment, that's why one resonance or one chemical shift, right? And then adjacent proton carbon have one proton, one, right? So 1 plus 1 2 doublet. And then this proton is split into how many, split into septate by 1 2 3 4 5 6 6 plus 1 7 7 neighboring 6 neighboring proton is split into septate. So this one also the proton NMR of isopropyl acetate, right? So how many different type of proton? 1 2 and 3. That's why it has 3 single 1 2 3. So the most shielded one is these methyls, right? And after this uh, this one, right? And right, so three different type of proton, right? And then this one is the most shielded one, second number, this one is the second shielded, and then most de-shielded one is this one because it's attached with the oxygen, right? So this one is split into doublet because it adjacent carbon have only one proton, this one, right? This one is split into singlet because it doesn't have any proton, so it is split into singlet. And then the most de-shielded one is this proton, right? How many protons nearby this, right? How 1 2 3 4 5 6 6 plus 1 7. This one is a septate, this one is a septate. That's how you have to explain the proton NMR spectrum of any compound. So these using the proton NMR spectroscopy to distinguish between the compounds. So you see these metals are ortho to each other. This one is meta to each other, and this one is the para to each other, right? So how many signal different type of the protons? 1 2 and 3, right? In this one compound, how many different type of the proton? 4. Why? Same chemical environment. 1 2 3 and 4, influence of this methyl, that's why it has different chemical shift. How many in this case? 1 2, right? Different these all four proton have same chemical environment, that's why 1 and 2, two signals. This one is 4 and this one is 3 because of the identical chemical environment here in these protons and identical in this one. So this is a concept map. So by this you can easily understood what is NMR spectroscopy all about and what are the important components in this: chemical shift, signal splitting, integration. Chemical shift tell us about the chemical environment, right? Chemical environment of the molecule. Splitting signal splitting tell us that the information about the adjacent proton. Integration tell us the number of the hydrogen atom produce a given signal, right? So in the chemical shift, de-shielding and shielding. Shielding is because of the presence of electron donating group. De-shielding is because of electron withdrawal group, right? Electron withdrawal group always come at high frequency. Electron donating group always shift the proton to the low frequency, right? And then the signal splitting, the formula is n plus 1, right? So if there is no proton adjacent, then it will be split into singlet. If one proton is split into doublet, if two proton is split into triplet, if neighboring carbon have three proton, then it will be split into quartet, right? So homotypic nuclei are having the uh, same compound if the substituted, right? And isotropic different protons, right? Diisotropic have lead to the diastereomer. So these are the different, so these are the things you have to remember in case of the proton NMR spectroscopy. So there are applications of the NMR spectroscopy. It is application in wider areas, right? In case of the chemical research and development, organic, inorganic, and physical chemistry, it has the chemical importance. It can Importance is chemical manufacturing industry, biological and biochemical research, food industry in order to identify adulterants and different chemical compounds in the food, pharmaceutical development and production, agrochemicals development and production, and polymer industry in order to identify the chemical structure of the molecules. So these are also some other common applications of the NMR. It could play a very important role in case of the structural elucidation, chemical composition, formulation, raw material, mixture analysis, sample purity determination, quality assurance and qualitative analysis, compound identification and confirmation, analysis of inter and intramolecular exchange process, molecular characterization, reaction kinetics, and the reaction mechanism. These are the most common applications of the NMR spectroscopy, right? So these the NMR spectroscopy also play an important role in pharmaceutical and biopharmaceutical analysis. In case of determination of the level of these APIs, the presence of the active pharmaceutical ingredients. It play a very important role in biopharmaceutical development, right? Including the identification of the biologics include protein, biosimilar, and these nucleotides, right? It are also used for identification of different nuclei, for example the proton, carbon 13, F19, and P31. Thank you for listening the lecture.